general physics, and Wiley resources, launch. We are in chapter 21. Okay. Okay, good. Magnetic fields, and we started looking at magnetic forces exerted on a moving charge. Okay, so that's where we are. Let's see, so far. So far, let's just a reminder, right? The lab report for lab 3 is due March 2024, just as a reminder. And also check if you can visualize your grades in Canvas, right? Note C, this is just a partial grade, right? It's a partial grade. And Sky is joining us. Please note C, just a partial grade. I am just a partial grade. So far, you have grades for the following activities, right? For the following activities. 1, exam 1, right? Attendance, lab attendance. Lab attendance for attendance for the following lab meetings, attendance for the following lab meeting. That, okay. Attendance for the following lab meetings. That was, and I want to, let me stop sharing momentarily. I want to make sure I'm not going to share a confidential information of yours. Wait. And now I can start sharing again. Attendance for the following lab meetings, February 7, 24. Right? February 14, 24. February 21st, 24. And that's what I have. Okay, for those meetings, I just gave you, if you attended the lab, you got 100%. Okay, for those 3 meetings. If you didn't attend, if you didn't show up for those 3 labs, you got 0, right? And if you show up partially, showed up partially, you got 50%. And I will be Pigo. So I will be posting the grades for lab, the grades for the reports of labs 1 and 2. I didn't correct the spreadsheet yet. So once I have corrected, I will be posting the grades for this report. Okay. What else do we have there? Exam 1 grades are already posted. The attendance for the labs were posted. Lab 1, lab 2, I haven't posted yet because I didn't correct it. Okay. Let's see. Grades for the homework. Will be posted at the end of the course, right? At the end of the course, because homework are due at the end. I also posted attendance. Oh, let's see what I'm doing here. Okay, like that. Grades for homework will be posted at the end of the course. Next, I posted the attendance grades, the lecture attendance grade, lecture attendance grade for weeks 1 through 6. Okay. It's a small, it's a small grade, only 5% of your grade, right? And Canvas, no, what else? Canvas automatically calculates your overall grade up to now. And that what on total, right? That would be the total. This total grade can either increase or decrease. So you can have a feeling of how you're doing in the course up to now. That's what I want to tell you. It's really, like I said, it's really nice that Canvas allows us to do that. So you can follow your grade as you go on. As we go on in the course. Okay. So that's what I want to tell you, and we can now move forward with the lecture. Okay, lecture for chapter 21. What we have done so far? Let's see here. Go, that's what I want. And notes. This one. It's not doing what I want here. What a shame. Let's see. Okay, now it's doing what I want. Good. Lecture for chapter 21. So far, we covered the following. 21.1 magnetic fields. This is an invisible entity we cannot see with our eyes, but we can measure it with equipment. Invisible quantity we cannot see with our eyes, but we can detect its presence with some devices, right? And then we start talking about the magnetic force. Magnetic force in a moving charge. This is also possible. This is also this is also possible to visualize with proper instrumentation. And the relation is the following, right? The magnetic force in an electric charge is given, that you have to memorize, is given by this equation here. Given by this equation, and where theta is the angle between the magnetic field vector and the velocity vector of the charge, This angle is measured when you put these two vectors tail to tail. That's how the angle is measured. Get those two vectors align tail to tail, place tail to tail, and the angle between them is going to be the angle theta. And here we covered that, right? And now the next one, more students coming in. Nope, not this one here. That I want to 14. Magnetic force in a moving charge. Force in a moving charge. So here you go. Charge is at rest, no magnetic force. Charge moving parallel to the magnetic field lines, no magnetic force. If the charge is moving perpendicular to the magnetic field, we have the largest possible force. And notice here, this is the velocity vector. I have to, let's see here. Strange. Let's see, we have to yeah, I cannot for some reason I cannot edit this image, okay? So here's the velocity vector of the charge. Here's the magnetic field. So this angle here is the angle theta that I mentioned before, okay? And here you go. We also have, okay, this one I can edit, that's good. Okay, here's the velocity vector and here's the magnetic field. So you put those two vectors tail to tail, and I'm going to illustrate that right here. I'm going to see it. Okay, this one. Everything else goes away. Oh no, I'm gonna need the velocity vector as well. I'm gonna need the magnetic field as well. Everything else can go, right? So here you go. If you have a magnetic field vector in this direction, I'll put it B here. I'll put the velocity vector. They have to be tail to tail, just like mentioned before. And then I still need the angle theta. Let's see. Yeah, this angle theta is not correct. Okay. I didn't put the angle theta in the proper way, but now I'm going to correct that. The angle theta is going to be this one right here. Okay. I have have to fix that in my drawing. The angle theta. I'm going to do like that, extend it, right? And now I can get the angle theta in the right way. That's the angle theta. Be better to increase it. Let's increase it in size. Gotta align it properly. Okay. I'm gonna make it a little bit thicker. And that's gonna be my angle theta. The velocity vector goes right in here. I don't need this dashed line here. Is the angle between the B field and the velocity vector, right? And I have it right in here as well. Okay. And as a result, we gotta cross V with B. Okay, and the resulting force is going to be perpendicular to both vectors. It's going to be perpendicular to this vector and perpendicular to this other vector. The resulting force is going to be illustrated as a vector like that. Okay, direction, I'll put it right in here. Direction of the force, let's put it this way. The dot here means that the force is coming out of the board. It's coming out of the board. Okay. Direction of the force. And don't forget the force is perpendicular to this velocity vector. Because the force is perpendicular to this velocity vector, it does not affect the speed of the particle. Okay, but it does affect its trajectory. Let's go back here. Here you go. The direction of the force, right? The direction of the magnetic force is given by the right hand rule. Because of that, now I can blow it up here. Because of that, the force, the magnetic force, will be simultaneously perpendicular to both vectors, both velocity, both the velocity and magnetic field vectors. Okay. Since the force is perpendicular to the velocity vector, comma, in a uniform magnetic field, comma, in a uniform magnetic field, the magnitude of the velocity, or its speed, right? Or its speed does not change. However, its direction may change. I put may, right? Because the velocity vector can be parallel to because the magnetic force can be zero, right? Its direction will change. Let's put it this way, will change if the magnetic force is different of zero. Let's put it this way, that's better. The force, the magnetic force, the magnetic force is always, will always, well, always be perpendicular if the magnetic force is different of zero, right? If the magnetic force is different of zero, better, is different of zero, it will always be perpendicular to the velocity vector. In a uniform magnetic field, does not change. The velocity, the magnitude of the velocity does not change. However, its direction will change if the magnetic force is different of zero. Okay, and what happens? And what happens to the direction of the velocity vector, right? Velocity vector in a uniform B field. So now we have an interesting situation. You already know that the direction of the force is perpendicular. Okay. Let's look at this one here first, right? This one here, that's this, no, not this one, sorry. Let's look at this one here. Yeah, okay. I'm gonna look at the simplest case. Here you go. The simplest case for magnetic force different of zero is this one right in here. Okay, that's the simplest case that we get. Velocity perpendicular to the magnetic field, theta equal to 90 degrees. Theta equal to 90 degrees. Superscript. Okay. That's why I put a little square here. That's the symbol for and now I'm going to put a little dot right in here. Fill it with the black, yeah, to denote a dot. Denote a dot. Yeah, that's the symbol for 90 degrees. I square with a dot inside. Under this circumstance, the direction of the force, okay, the direction of the force is going to be pointing towards you, and very important too, I didn't mention that before, right? Provided the charge is positive, right? Direction of the force, provided Q is greater than zero, right? I need to add that. Direction of the force provided Q is greater than zero. If Q is less than zero, then the magnetic force is into the board. The magnetic force is also be given by, in this case, QVB. QVB. Subscript. Like that. That's italicized, so it looks nice. Okay. And now we can repeat that for a charge less than 0, for a charge, if the charge is a negative charge, the magnitude of the force is still going to be the same, but it's just the direction that's going to change. The direction is going to be into the board. Right here, that's the one I want. And here is the back of the arrow, right? I'm gonna make it a little bit thicker, yeah. And oops, and replace this guy right in here. Nope, I don't want to get rid of that. I want to get rid of this one only. That's the direction of the force. Direction of the force, provided Q is less than 0. So the direction changes if we change the sign of the electric charge. Okay, and the same thing applies here, right? You go direction of the force and direction of the force provided Q is greater than 0. In this specific case, the force is going to be sine of theta. Symbol. Sine of theta. And we get exactly the opposite direction, right? If the charge is less than 0. Direction of the force provided Q is less than 0. More students coming. And now we are ready to talk about the path of the particle. We're ready to talk about the path of the particle. More students coming. Now I'm going to change the view, okay? Right now, the magnetic field is in the vertical direction of the plane of the screen. But now I'm gonna change the view. Instead of having the magnetic field in the vertical direction, I'm gonna make the magnetic field pointing away from the screen, from my screen. Here's my axis, X and Z. I call them X and Z. I'm gonna make it a little bit nicer, make it black, okay? Previously, we had the X and Y here. Let's see. This one here, in this case here, we had the axis was what? Let's get this axis here. The Y is parallel to the B field. The Y is pointing in the same direction as the B field is pointing. Okay. So what we had here before, here was Y, right? But then the X is on the other direction. Okay. Because why is that the X is in the other direction? X is in the other direction because it's opposite to the velocity vector. Okay. X cross let's see. Oh, well, wait a minute. I did a mistake here. No. Is the B. Okay, is X is correct. The Y is incorrect. The Y has to be downwards. Okay? The Y has to be downwards. That would be the right one. And of course, the Z is coming out of the page. Okay. So here you go. X anti-parallel to the V vector, to the, let's see, yeah, anti-parallel to the V vector. If you do the right-hand rule, Z cross B, the Y-axis is into the board. Okay. And now we just change it, change it the angle of view of the previous drawing. And what we end up getting, here you go. B is pointing towards you, right? Velocity vector V cross B. V cross B, the force is in this direction, the Z direction. I'm gonna put this force vector, velocity, the force vector like that from the center. I'll put the velocity vector, bring to the front. I'm gonna put it like that as well. And now, and I'm going to dash this one here. Why is that? Because it's the path of the particle, okay? In a uniform magnetic field, magnitude of B field equal to the magnitude here is equal to the magnitude of B field here, equal to here, and so on. This particle is subjected to the same magnetic force anywhere in the space. And then what we have? We end up having a constant magnetic force that's always pointing, the constant magnitude of the magnetic force that's always pointing perpendicular to the velocity vector. Okay, that's the case of B perpendicular to B. Case of V perpendicular to B. And then because of that, the particle undergoes a uniform circular motion. Okay, so here you go. At this instant of time, it's here. A little bit later on, it's here. Okay, and I can fix my magnetic force just like I did before. Velocity vector, bring it to the front. It's not obeying me, because I'll copy this one. And now it's gonna work. Good. And now make it perpendicular to the force vector. I don't need this guy anymore. Okay. Okay, so at a given instant of time, it's here. A little bit later on, it's gonna be here. And then we can keep on coming up with different positions so we can animate, right? Can animate this situation. Did you get the idea? And don't forget, this one is for V perpendicular to B. Okay, and I'm gonna write that down here. V perpendicular to B. V perpendicular to B. Uh, doesn't fit here. I gotta change the size. Yeah, perpendicular to B. Be perpendicular to B. Okay, and then we can go back there to my notes. What happens to the direction of the velocity vector in uniform B field? Okay. Okay, so A. If V is perpendicular to B, comma, the charge will undergo uniform circular motion. And don't forget uniform B field. I'm going to emphasize here uniform B field, uniform circular motion. Now, if B is not perpendicular, right? If B makes an angle different of 0 and 90 degrees, comma, then the charge will move in a spiral fashion. Okay, so what's going to happen is it's very easy to visualize what happens here. Now suppose that the velocity vector makes an angle different of 90 degrees with the B field. Okay, so we can go back right in here, right here in this figure. See, in this case here, there's an angle theta here. Notice that we are going to have a component that's perpendicular to the B field and another component that's parallel to the B field. Okay. The particle still will undergo a circular motion, but there will be something else happening here. Because the particle has this vector velocity component parallel to the B field, the particle is going to undergo a spiral motion along the magnetic field. Okay, that's what's going to happen. So we can document here. If V makes an angle with B different of 0 and 90 degrees, then the charge will move in a spiral fashion along the B field line. Let's take a look. It's a little bit difficult to illustrate that. So let's see if we can find an illustration here in your book so you can have a better visualization how it looks like. Motion of charged particles in the magnetic field. Okay. Force, right? So here, let's see. Here you go. That's the motion. That's the arc, a circular arc. Uniform magnetic field here. We insert a positive electric charge here in this field, and it's going to undergo a circular motion while it's subject to the field, right? Now let's see if they have an illustration of the spiral motion. Here you go. Same illustration that I put for you there in the another student coming in. Unfortunately, it doesn't look like we have it here. Yeah, we do not have it here. So we have to look at the internet. Let's take a look at the internet. Let's take a look at the internet. We will certainly have one of those out there. motion of a charged particle in a uniform magnetic field. Okay. Let's try this one here. Let's see, Professor, can you send me? Let's see. It's not showing any of the illustrations here. What a shame. Let's go back here. Let's see if this one has magnetic field. Here we go.
Let's explore how to calculate the path taken by a charged particle in a magnetic field, and then we'll be able to answer why these beautiful auroras are only seen by people at the poles. That's right, the time these people can see spectacular light shows in the sky, but what happens at the poles? We'll be able to answer that question later. All right, so let's start with a case where you have magnetic field into the board.
Let's watch this one.
And uniform into the board. And let's consider a charged particle, let's say a proton, that's moving perpendicular to the field.
A proton.
We'll start. Let me just write that down. Let's consider a case where particles are moving. Let me just draw it over here. So let's say we have a proton that is moving perpendicular to the field. So the field is inwards. Let's consider the proton going upwards. So the case we're dealing with is velocity of the charged particle is perpendicular to the magnetic field. I want to now know, in this case, what's going to happen to the proton? How will it move? Will it keep moving straight or will it turn? What's going to happen? What is the path that will be taken? How do we calculate that? Well, to calculate the path of any object, we'll have to figure out the force acting on it. And we've seen before, the force acting on.
So try to figure out what's going to be the direction of the force, right? You should know that already, right? You do the right hand rule, right? V cross B, the force must be from the right to the left. Okay, and in this case, the V is perpendicular to B, is going to be just circular motion. That's all. But then, what if V is not perpendicular to B? Okay, he has a situation here. Okay, so here's another way of illustrating the circular motion of the particle. It's still perpendicular, right? Another way of looking at the, yeah.
What if we have magnetic field to the right? Like
here you go. Now we are here orienting the magnetic field so you can see the path of the particle.
And let's say we have a proton that is
of the charged particle
moving downwards.
So here you go.
Again, notice the same case. We have velocity.
It's still perpendicular.
But now I want you to use your right hand rule. Think about which direction the force is going to be, and think about how that circular path is going to look. This is going to be in 3 dimensions, so you'll have to visualize a little bit. So why don't you pause the video and visualize what will the path taken by the particle. All right, hopefully you've tried. Let me bring in my beautiful right hand, and I'm going to orient my right hand this way. Again, notice my 4 fingers must be pointing in the direction of the velocity, and I'm pointing in such a way that I'm going to curve my 4 fingers in the direction of the magnetic field. My magnetic field is like this, so now I'm going to curve like this. You see that? Here we go, curve this way. And as a result, notice the thumb will point out of the screen. And so from what we learned over here, this means this particle is also going to go in a circle, but the center of that circle is going to be somewhere out of the screen. So can you visualize what that circle is going to look like? Let me get rid of this hand. So this particle is going to go somewhat like this. Let me draw. It's going to go this way. It's going to come out of the screen. Yeah. So like this. Again, it's going to go into the screen. It's going to go in a circle like this. It doesn't look like a circle, but that's what it is. So here will be the center of that circle. Yeah. So Again, circular path.
He's doing a 3-dimensional drawing, a 2-dimensional board, right? That's what he's doing here.
Particle will go in a circular path. So this is how you figure out the path taken. But now let's consider a more general case.
More general case.
Over here. What if I have a magnetic field like this? And let's consider that same proton, charged particle, proton, whatever that is, but it's not perpendicular to the magnetic field. Let's say it's moving at an angle.
Angle. Here you go.
Interesting. What's gonna happen now? How do we figure this out?
Okay, remember what I told you, right? Here you go. You have the component of the velocity that's parallel. In this case, is anti-parallel to the B field. Okay, this component of the velocity does not experience add any magnetic force to the charge, because this component is anti-parallel to the B field. But what is left of the other component is the one that affects the motion of the particle, is the one that will make it undergo uniform circular motion. Okay? But because we still have this component that anti-parallel to the magnetic field, the particle not only is going to move in a circular path, but will also be dragged, in this case, to the left, which will result in a spiral motion. That's what this guy is going to tell you, okay?
Well, the way I like to think about it is I already know that if the particle was going perpendicular, I know it's going to go in a circular path. So what I'm going to do is divide this velocity into two components, one that is perpendicular to the field and one that is parallel to the field, and look at what will be the path for each of the components. So we already know for the one that is perpendicular, it's going to be a circular path. Let's now figure out what happens to the path when the charged particle is moving parallel to the magnetic field. And again, we're going to do the same thing. We're going to first figure out what the direction of the force is, and then from that, we're going to figure out the path taken. Again, why don't you pause the video, use the Lorentz force, and think about this. What would be the force acting on a particle if it was going parallel to the magnetic field? Pause and try. All right, let's see. Because you're doing a cross product, remember that cross product becomes 0 when vectors are parallel or anti-parallel to each other. So because this is going parallel to the magnetic field, it experiences no force. So this component will just go in the straight line with the same speed, unaffected. This component will try to make the particle go in a circle. So what's going to be the net effect? Well, one is trying to make it go in a circle. Another one is trying to make it go forward like this, the opposite direction. And so together, you're going to have a circle that's going forward. Let me try and draw that. So together, we're going to have a circle. Let's use blue. Okay. A circle that is going forward. Something
the spiral
like
motion.
This. In other words, this is going to be a helical motion. So in general,
Helical would be the better.
In general, what we find is particles tend to go in a helical path. And look at the helical path. The axis of the helical path is the magnetic field. You see that? And the circle, the plane of that circle is going to be perpendicular to the magnetic field, just like what we found over here. All right, let's do one last example. What if we have magnetic field this way? And imagine there's now an electron. An electron is going in some random direction. Let's say electron is going this way. Can you pause and figure out what would be the path taken by this electron? All right, let's see. We're going to do the same technique. I'm going to decompose this velocity into two parts. One perpendicular to the magnetic field, one parallel to the magnetic field. I know this parallel component tries to keep this electron going in the same direction. Let's see what the perpendicular component tries to do. Well, velocity is upwards, magnetic field is towards the right. And so if you use your right hand rule, I hope you can do that yourself now. I don't have the picture of that available. But if you use your right hand rule, the force, the thumb would point inwards. Okay? But remember, this is an electron. And so if you have an electron, there'll be a negative charge over here. And so you have to flip the force. That means the force will act out of the screen. And so the center of that circle is also going to be out of the screen. As a result, the way I visualize this, the circle is going to be like this. The electron will come out of the screen, go into the screen, come out of the screen, but at the same time, it's going to go forward. And so the net motion will be a helical path that will look like this.
There you go.
This is not a great helix, but you get the point. This is how it's going to go. All right, now let's see why we only get auroras at the poles. It's got something to do with.
Okay, what's the application of this type of motion? There is a very nice application for this type of motion, okay? So you got the idea, right? The helical path. You get an helical path if the velocity vector of the charged particle has a component that's parallel to the magnetic field. And there is a very nice application of this knowledge to the case of auroras that we observe in the nearby the northern latitudes, okay? And don't forget the magnetic field of the south and north magnetic pole of the Earth is very close by the north and south geographic pole of the Earth. So it looks just at the magnetic field source just look just like that, right? Here's the north magnetic pole, here's the south magnetic pole, which is nearby the south geographic pole and the north geographical pole. Okay, in the interplanetary space nearby the Earth, we have lots of charged particles that comes from the sun. That's the solar wind, okay? And those charged particles, they usually get trapped in the magnetic field of the Earth. And what's going to happen? You know, if they get trapped at a velocity vector that is not perpendicular, right, to the magnetic field, what's going to happen? Magnetic field lines of the Earth, what's going to happen? Those charged particles are going to spiral towards either pole, either the North Pole or the South Pole, okay? That's what's going to happen. And when those charged particles start to enter the atmosphere of the Earth, when they encounter the molecules of air, the nitrogen, the oxygen, the carbon dioxide, a little bit of carbon dioxide there, right? They are going to collide with those molecules and make those molecules glow. And that's what produced the auroras on the Earth, exactly because of this helical motion of the charged particles, either towards the North Pole or the South Pole. It all depends on the velocity vector of the charged particles. Okay? And that's what this guy is talking about.
Field of the Earth. So turns out that sometimes your sun, everybody.
I'm going to accelerate a little bit.
It launches charged particles, and these charged particles, once they enter into the magnetic field, they get trapped. Because once they enter the magnetic field, they start following the field in a helical path like this. So they'll start following the field like this in a helical path. And eventually, they will follow all the way towards the poles, and notice that's where they enter into the atmosphere. The same thing could happen on the other end as well. So if the charged particle gets trapped over here, it will follow the field and enter into the atmosphere only at the poles, because that's where the magnetic field starts and ends. And when these charged particles enter the atmosphere, they interact with the atmosphere, causing these beautiful auroras. And that's why you only see them at the poles.
And don't forget, all those auroras that you see here is a result of the interaction of the charged particles with the molecules on the Earth's atmosphere. And the colors of the aurora depends on the molecule that the charged particles interacting, okay? If the charged particles interacting with the oxygen of the Earth, you see one color. If the charged particles interacting with the nitrogen in the atmosphere, it's gonna be a slightly different color, and so on, okay? That's the piece of information that I wanna tell you. And there is one more thing that I wanna show you. It's possible to visualize this type of interaction in the lab. We do have equipment there at the Lake Harbor that can be that make it possible for us to visualize the path of a charged particle in a magnetic field. Okay, But before we go into that, let me just add something to my notes here, right? If it makes an angle, then the charge will move in a spiral, not a spiral, it would be in a helical path along, we move along a helical path. We'll move in a helical path along the B field lines, okay? The auroras that we see in the nearby the north and south poles, geographic poles, right? Geographic poles of the Earth is the result of charged particles in the interplanetary medium that comes from the charged particles in the interplanetary medium that comes from the sun, okay? That come from the sun. Those charged particles are part of what we call the solar wind. That get trapped in the Earth's magnetic field. Okay. In this case, once they get trapped, they undergo an helical path towards the north and south poles of the Earth. Okay, and that depends, the direction of motion depends on the velocity vector, right, of the particle. The auroras that we see nearby the north and south geographic pole are the result, right? Are the result of the interaction, let's put it this way, of charged particles from the interplanetary medium that comes from the sun. Planetary medium with the Earth's atmosphere, I'm going to just change a little bit. These charged particles become trapped in the Earth's magnetic field and undergo a helical path towards the north and south pole of the Earth. Once they collide with the molecules in the Earth's atmosphere, this collision produces a glow that is seen as the auroras. Okay? That's the type of nice application of this phenomenon that you see right in here that we study. And okay, and now what I want to do, I want to take attendance. Okay. Lecture, and today is the 18th. Jacqueline Hernandez, are you there, Jacqueline? Okay, thank you, Jacqueline. Sky, are you there, Sky?
Here.
Thank you. Vanessa Escalera. I think Vanessa Escalera has dropped. Let me take her out of here. Ashley Izumo. I don't see Ashley here in my list. Corina, are you there? Hello, Corina. Corina Jurado. I'm going to put a little star. Oh, okay. Thank you, Corina. Norberto Lopez.
I'm here.
Thank you, Norberto. Vanessa Mena.
Here.
Thank you. Yorgo.
Here.
Thank you. Lizelle. I don't see Lizelle. Oh, Lizelle is here. Good. Thank you. Paul Zapata. He's also here. Thank you, Paul. 8 students who didn't show up. Ashley is the only one who didn't show up. Right. And okay, we're gonna go for a break. Any questions about that? When we come back, I'm gonna show you some videos that allows you to visualize the path of charged particles. There is a way to do that. We have equipment to do that in the lab, okay? I'm gonna even put next, when we come back, when we return after the break, okay, I will show you some videos that allow us to visualize the path of charged particles subjected to an electric and magnetic field. It's a really nice experiment, that I like to show my students when we do that in person. But I'll show you when we return, okay? And we're gonna go for a break from 10 a.m. to 10:15 a.m. Okay. And I understand that you don't have the link for your group folder, is that right?
Yeah, I don't know what happened, but I was only able to do see the lab one too. I thought I downloaded it, but I guess I haven't downloaded the official file link.
Okay, and what's your group number? What's your group number?
I think it's 2. I'll double check with the team.
Let me check. I can check it here too. Don't worry. Yorgo, Yorgo. Group 1. You're group 1. Yorgo. With Lizelle and Paul, right?
Yes.
Okay, let me get that for you. And I will. Don't forget, we keep this link in a safe place so you don't lose it. Google Drive. And Drive. Group 1. Share, copy link. Okay, and that's your link here. And group 1, here you go. Lab 1 and 2, right? There's lab 3 here as well. This one, I upload this one here. Those
So all I have to do is just click on the link, and then whatever lab I'm doing is I'll just download it to be able to write on it, right?
yeah, and you're trying to it would be, you want to download or upload?
No, what I'm saying is when I use the link and I access the lab 3, when I'm gonna work on it, I have to download it, right? First, I have to download. Yeah.
Yeah,
Okay.
that's right. Okay, so I'll see you in, lab 3 is right in here. Okay, lab 3 is right in here. So I see you in 15 minutes. Okay, stop sharing. back. I got here something for you, and it's possible to create an aurora in the lab, okay? Something similar to aurora. And that can be done with what we call the Crookes tube, which is a very nice device that we can use to demonstrate the deflection of charged particles by a magnetic field. We have this device there at LA Harbor. And here you go. I'm going to show you a video in YouTube that show one of those Crookes tube. Here you go. Here's the Crookes tube right in here. We have one of those there at the LA Harbor. What you see here in the back, this yellow box in the back, is the power source of the Crookes tube. It's a high voltage, 5,000 volts. And you gotta be careful about handling this thing. Okay, and let's take a look at this video so you can see how it works. I will try to do some explanations along the way as he describes. You go, electron beam in a magnetic field, okay? And what I gotta tell you is that this Crookes tube is capable of generating electrons, an electron beam, from one of those two terminals. We also have a potential difference here between those two ends that accelerate the electron from one place to another one, okay? And people came to the conclusion that those particles were negatively charged after experimentation in the 1800s. That's when the Crookes tube was invented, which later on evolved to what we call today the cathode ray tube. The cathode ray tube that was used in the early TV models and the early computer screens as well. Nowadays, we don't use CRTs, cathode ray tubes anymore because they're too bulky. Today, we use the flat screens, right? The LCD screens, the LED screens, the OLED screens, and so on. So let's take a look
I
here.
can actually show you that with a real charged beam. So this is an evacuated tube, and it puts a big negative potential.
Okay, don't forget that the evacuate tube, that's what the Crookes tube is all about. It's not exactly evacuated, okay? Because if you're going to see something, a greenish, oh, this one is not a greenish, this one is a bluish, okay? If you see a bluish glow, that's because you have some molecules here inside that glows as the electrons are emitted from this end to the other one, okay? Take a look how it is. Remember that that's the black terminal of the power supply, which is the negative one, and that's the red terminal of the power supply. That's the positive end. And don't forget, this box here is a high voltage box. And again, the electrons are emitted from this end. Notice that we have a little slit here. This is what you see right here is a metal. The metal is a slit. Why this is slit in there? This is slit in there is to ensure that only the electrons that are moving in a straight line goes through. If you have electrons being emitted at a high angles, those electrons are stopped by this screen here, by this metallic screen, okay? And let's go ahead, let's keep on playing.
On this electrode, so high that it actually boils, the electrons come off the electrode. It makes just a beam of electrons. It also has some ionized, a little bit of background gas that ionizes.
Okay,
stable.
So see, it's not an evacuated tube. It has some gas here inside. The gas is in there so we can visualize the beam of electrons. Those beams of electrons are going to collide against this gas that's there inside, just like happened in aurora, right? And those gases end up glowing due to the collisions of the electrons with those gases.
It doesn't charge up too much. But mostly you have electrons flying up this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate. So some of them get through and make a beam that keeps going. So you've got a beam of electrons. And this little plate is tilted a little bit. So they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into it.
In addition to the gas, okay, we also have this white plate here that has some phosphor material. This phosphor material, when the electrons collide with this phosphoric material, they also glow. Okay, that's the idea of putting this plate here with the phosphor. And what that was exactly how the CRT tubes were made of. They are made of phosphors that were in the screen, and a beam of electrons would collide against that phosphor, producing the glow, the phosphorescent, right?
Wait, so when I turn it on,
Here you
you
go.
can see the beam. That's a beam of
Here's the
electrons.
beam. That's how we visualize the electrons. The electrons are invisible particles, but if we are smart enough, we can find ways of visualizing those invisible particles, right? The beam of electrons, he turned it on, and now the electrons are coming from this terminal, moving towards the other one.
It's flying through the tube. So what we're going to do is bring a magnet.
Okay, he has now a magnet, and he will demonstrate that this magnet is capable of altering the path of the beam of electrons.
And see what it does to the beam of electrons. Because remember, this bar magnet, the field lines go from the North Pole, the red is the North Pole, to the South Pole. So if we just think about the poles or the field right at the ends, because we're going to use the ends, it'll be this way near the north, it'll be pointing in the south. So I will bring the North Pole pointing at me at the beam. Let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So B cross B also the same as this. It should be up. So let's see what happens. There's our beam, and I bring in this magnet. Oh,
Okay,
there's the deflection we hoped for.
see the deflection?
Down. It's down. Why? is it
That's
down?
what happens whenever you
Because they're
subject.
electrons.
That happens whenever you subject the beam of electrons that are flying with a given velocity, okay, to a magnetic field.
Oh, there's the
There you go.
deflection.
Without the magnet, the beam is flying straight. But when you put the magnet in there, the beam is bent. Okay, and then you can do the right-hand rule here, okay? Don't forget, this is a negative electric charge. You have the velocity vector from the left to the right. Let's say this one is a positive, right? We gotta cross the V with the B, right? The V with the B. We are getting a V cross B is upwards, but because this beam is negative, so the direction of the force is downwards. That's why it's deflecting it downwards. That's why the magnetic field is deflecting the beam downwards.
Deflection we hope for, but it's down.
And if you change the polarity, you're going to see that the beam is going to be bent upwards. If you change the polarity of the magnet.
It's down. Why is it down? It's down because they're electrons. Q, in this case, equals negative E. The charge is negative. When the charge is negative, the force magnitude is negative, which means it goes the opposite direction. Right? So right-hand rule says it's up for positive, but the force is down.
Because of the negative.
So it did deflect the right way. It deflected down. We can also check, we can take and aim the South Pole at the beam.
The South
There we
Pole.
go. Bring in the South
There you
Pole.
go.
And there we
Bending
go.
upwards.
Up. Just like you'd expect. When you bring in the South Pole, the beam, or the magnetic field, is pointing the opposite direction.
Now imagine those guys back in the 1800s doing this experiment for the first time, right? And they were still trying to make sense of the things that we already know today in the 21st century. It was like 150 years ago that they start playing with this device, with the Crookes tube.
I'm bringing in a field that's pointing away from the beam. So it would seem that the charged particle beam really is deflected the direction that you would expect.
Okay, and there are other videos too that you can Crookes tube right here.
So what we're gonna do is I'm gonna be like the fast moving object with the,
Here you go. Let's stop this guy. We have more, here you go, a green glow, right? Oh, here you go. Another green. That other one was blue glow, right? The one that we have at the Lake Harbor was a green glow as well. And here you go. Let's take a look at this one.
So what I'm going to show you today is how we figured out that Dalton's model was not complete. And it began with this thing called the Crookes tube. Has anyone seen a Crookes tube before? This is a Crookes tube. What it is, it's a tube of glass that's mostly.
It's very important to note. I'm going to point out, that's how X-ray was discovered. Okay, X-ray was discovered with those Crookes tubes. And people, a guy was performing an experiment with electron beams, and they put so much energy in the electron beams that he was able to produce an image in a photographic plate. And he came up with the idea that maybe there is some sort of different radiation that we cannot see by the naked eye. And he christened that radiation X-ray. And X-ray was kind of a revolutionary discovery and invention too, because it allows us to image the body in the inside. Marie Curie, she worked with X-rays during the First World War. It's a fascinating story what she was doing. Not only she got the Nobel Prize for the discovery of radiation, but also she worked during the First World War with X-rays to image broken bones inside the soldiers of the war that was fighting the war.
It evacuated, meaning most of the air is taken out of it. It's got an electrode on this side and an electrode on that side. If you look on the inside of it, there's a white screen, and the white screen is there for reasons I'll show you in a moment. This is a Tesla coil. Tesla coils generate lots of voltage.
Okay, there's another way of producing an electron beam, okay? That guy used that power supply, very high voltage power supply. What he's going to do, he's going to use a Tesla coil instead to generate a beam, an electron beam here in this device. You're going to see how he does that. Here you go.
Right now there's a magnet inside of here that's spinning, and it's got some wires around that magnet. It's generating a lot of voltage as it spins because it's a strong magnet. In fact, if I hold another magnet up here, I can feel it vibrating from the spinning of the magnet. Kind of like your rumblers on your game controllers. And but this is generating a lot of electricity. You can see that if you hold it up to something level. People always ask what will happen if we touch it. The answer is you'll die. Why I am now dead. A little bit uncomfortable. But in any case, here's what happens when you hold it across the Crookes tube.
Yeah, here you go. See the glowing, the green glowing?
I see that. You see it over there on that side. Like this. Pretty cool.
The electron beam.
I actually can't see it from my side, but I assume you're seeing a straight green line.
Yeah, the electron beam passing through this slit, right? There are electrons flying all over in every possible direction, but only the electrons that are flying straight into the slit are the ones that pass through. Okay, if we didn't have this slit here, just we would have this plate would be completely glowing green everything here would be glowing green, but now that we have this slit, only a very small line of glowing. You see only a small line of glowing here. That's what this slit is all about.
Mostly. Because I'm looking from behind. That white screen's only on the front. It's set up to be viewed from one side only. All right, now, this is kind of interesting. Watch this.
Okay, that's the magnet, right? That's the magnet. That's deflecting
Anything happening?
the path of the charged
What's
particle.
happening? And it's following the magnet, reacting to the magnet, it's deflecting the magnet. Okay, so that's kind of interesting. Keep that going. I got a one other thing to compare that to. I have a light here, and I'm going to pass this light, it's a laser light, green laser light up here. You see that that laser light, see it there? What will happen to it when I get it close to the magnet? Deflect away. It's deflecting away. It has no effect on the magnet. The magnet has no effect on it. So why did some light get deflected by a magnet and some other light doesn't? Why is that? What's the primary difference?
Oh, we can stop it here. So now you got the idea, right?
Why?
So magnetic, that's how we can see, right? What is invisible. Those are ways to see the invisible world by doing some little tricks, right? And let me, I'm gonna talk about one way, here you go. One way to visualize a beam of electrons is by using what we call the Crookes tube. Okay, the Crookes tube was the predecessor of the cathode ray tube, the CRT, which was used as an imaging device for TVs and for TV screens, computer screens, and other devices, okay? Until the year 2000, when it was replaced by the LCD and LED and OLED screens. Okay. The CRT screens were very bulky because they needed a relatively large distance, right? Relatively large distance to propagate the electrons. Okay, so one way to visualize a beam of electrons is by using what we call the Crookes tube. In the Crookes tube, we have two polarities, right? Negative and positive, that we connect to a high voltage source. this high voltage source creates an electron beam and accelerates it between the two terminals. Okay, so it's gonna be something like that. I'm gonna draw, you know, it's gonna be something like that. Here you go. The Crookes tube is not like exactly a plate, right? The Crookes tube is not a plate. It is more like a terminal. That tip that you saw. This one is negatively charged. We're connecting, right? It becomes negatively charged because we connect those two leads to a high voltage power supply. And now we can eliminate that. Go. Like that. And then we have the same thing here with a positive sign on the other end. We must have a container here, a glass container, right? So no fill. Because we have a power supply connected to those two electrodes, we have an electric field from the right to the left. I'm gonna erase that stuff, right down here. Simple, Crookes tube. Okay, and then we put a slit right in here. Let's see how I'm gonna draw my slit sideways, right? Like that. The upper portion of the slit, the lower portion of the slit, right? And a beam of electrons goes through I'm going to put my electric field like that so it doesn't overlap with my beam of electrons. I'm gonna put it in a green color, this beam of electrons. Yeah. like that, electron beam. Did you get the idea? I gotta put also the power supply here. Black terminal. Black terminal here. And the other one is gonna be my red terminal. And my cables. Connected to the electrodes. This cable here is gonna be black. Gonna make it a little bit thicker. Yep. And the other cable here is gonna be red. That's a very simple drawing explaining the Crookes tube, how it works, right? I'm going to emphasize that this greenish beam here is my electron beam. Okay. Change a little bit. I got 28. Too small. I'm gonna put it in green color, so electron beam. This one goes away. Oh, not this one here. Here you go. Okay. So that's a simple drawing how the Crookes tube, the pieces of the Crookes tube, right? How it works. I didn't put this to the phosphor screen there. Going back. Okay, in the Crookes tube we have two polarities, negative and positive, that we connect to high voltage source. This high voltage source creates an electron beam and accelerates them, the beam, right? Between the two terminals. A screen with a phosphorescent substance is used to visualize the path of the electron beam. Okay. By approaching a magnetic bar, we observe a deflection of the beam of electrons due to the magnetic force. Okay. That's what I want to share with you. And now I want to move forward with other things. Here you go. Motion of charged particle in a magnetic field. Now you know how the charged particle moves in a magnetic field. And there are some interesting devices out there that the book covers. One of them is the mass spectrometer. But before we talk about the mass spectrometer, I'm going to talk about a simpler device that is the velocity selector. Yeah. Here we go. Yeah, let's talk about before we talk about the mass spectrometer, let's talk about the velocity selector. The velocity selector is a much simpler device. Okay. It starts with a 2 plate. And velocity selector. Two parallel plates. And you know that there is a uniform electric field here between those two parallel plates. But then we do something else. We add a magnetic field here, perpendicular to the electric field. Okay. Uniform electric field, uniform magnetic field, perpendicular to each other. And then what else do? We put a charged particle within this volume, within this region. Let's start with a positive charge. Okay. This positive charge, if it's at rest, you will experience an electric force that will attract it towards the negative plate, right? But if we go ahead and put this charge to move with a given velocity, if the charge is at rest, there is no magnetic force, just one electric force, right? Just electric force. And the charge will be attracted to the negative plate of the battery. But if we impinge a velocity vector perpendicular to the magnetic field, perpendicular to both the electric and magnetic field, we are going to have a magnetic force as well. You go ahead and you do the V cross B vector. Don't forget it's a positive charge, right? And we end up getting this magnetic force to the right, electric force to the left, magnetic force to the right. Okay. If the velocity is just right, the net force applied to this charge is going to be 0. Okay. If the velocity is just right, the net force is going to be 0, and this particle is going to move in a straight line until this detector here, that can be our phosphorescent screen that you saw before. Okay. If the velocity vector is not just right, then the particle is going to be deflected either to the right or to the left. Make sense? Okay. And that's why this device is called the velocity selector, because it's capable of selecting charged particles of a given velocity. If you adjust the electric and the magnetic field, you're going to let particles only of a charged particle, only of a given velocity, to travel in a straight line towards the detector, towards this detector, okay? If the velocity is different, the particle is going to be deflected either to the left or to the right. Make sense? Okay, and we can go ahead and play with the equations. Velocity selector. Components, right? Components. 1, 2 charged plates, parallel plate capacitor, same. Two charged plates, one positively charged, the other, two charged plates, one positively charged, and the other negatively charged. Negatively charged, producing a uniform electric field between them. Okay. A uniform magnetic field perpendicular to the electric field. Okay. 3. A charged particle at rest within this volume will be attracted towards the negatively charged plate, right? A positive charge plate, a positively charged particle at rest within this volume will be attracted toward the negatively charged plate. However, if the charged particle has a velocity vector simultaneously perpendicular to the E and B fields, right? It will be subjected to an electric and magnetic force. To an electric and magnetic force, right? If the velocity, if the speed, right? Speed of the charge is just right, we will have, it will be subjected to a zero net force, or like that, you know? And that's if you have the right, right? Here you go. The magnetic force is going to be QVB, right? The electric force is going to be QE. If this velocity is right, it's just right, we can have a net force FE plus FB, which is, by the way, equal to QE plus QVB equal to 0, right? The Q cancels out, right, from both sides. Here we're supposed to have a negative sign, don't forget, the negative sign here. And I'm going to put let's put a vector, right? Let's put a vector. That. I'm going to get, here you go, X. Yeah, let's put X hat here. X hat and X hat. Right? So in order to have a net force equal to 0, the velocity of the particle must be the following: E divided by B. Okay. So we can do that just by adjusting the electric field, right? By adjusting the amount of charges in the plate, and also by creating a magnetic field that will give rise to the net force equal to 0 for this charged particle. Notice that the charged particles that have this specific velocity will be subjected to a net 0 force, right? 0 force. And they will fly, they will move, right? They will move in a straight line. So we can use those devices to filter out charged particles, and by the way, irrespective to their charge value, irrespective to their charge value. It can be an ion as well as an electron. It doesn't matter. It doesn't matter what's the amount of charge that the particle is, provided the velocity is the same. Okay? Particles are undeflected, provided charged particles are undeflected, provided their velocity are the same, their speed are the same, right? Speed are the same, and irrespective to their charge value. Okay? Is respective to their charge value. Okay. So that's how the velocity selector behaves. That's how the velocity selector behaves. We need the velocity selector before we go ahead and start talking about the mass spectrometer. Okay. And by the way, what I'm going to put here, here's my detector. I'm going to put my detector a little bit far away. It can be larger because we may have other particles with the right velocity filling this volume, right? If the velocity is not right, they're going to escape through this two gaps here on the side. There is one more element that I didn't put there in the speed of the charge. Okay. Two charged plates, one positively charged, one positively charged, the other negatively charged, producing an uniform field, a uniform magnetic field, right? And don't forget a phosphorescent screen used as a detector for the charged particle. Okay, and now we can start talking about the mass spectrometer. Remember that a particle, charged particle, undergoes a uniform circular motion when subjected to a magnetic field, right? Here it does not undergo a uniform circular motion because we have another force there. We have an electric force, right? An electric force right in here is preventing my charged particles to undergo a uniform circular motion, right? But what if we have a magnetic field that stands beyond that volume, right? Let's see if I can get here oh yeah, right here. That's the one. A new device, the mass spectrometer. In the mass spectrometer, let's see. The mass spectrometer. The mass spectrometer is a combination of a velocity selector with an external magnetic field. It's an external magnetic field. No external E field, okay? The field is only in the inner volume of the velocity selector. Velocity selector. Here you go. Only is in the inner volume of the velocity selector. So here you go. Here's my velocity selector, right? Don't forget I have to put a little gap here in between. So those particles that are not going through this gap, they escape, right? And so what happens? Once the particle leaves the volume of the velocity selector, it will be subjected to this magnetic field. Okay? Here you go. Here's the particle exiting the velocity selector. Now it's subjected only to the magnetic field, the outer magnetic field. And what's going to happen? If it's a positively charged particle, V cross B is going to make it turn to the left, a circular motion to the left. Okay? And what we have here again is our phosphorescent screen. And we can find out what's going to be the charge to the mass ratio of this particle when we perform an experiment like that, okay? So this particle, whenever it undergoes this uniform circular motion, eventually it's going to strike this screen, and you will be able to see where this particle struck the screen because it's going to glow. And then you can go ahead and measure this distance here. That's going to be the diameter of the orbit of the particle. And we can find out what is going to be the charge to mass ratio. Okay, and let's do that. Let's see how we can find that out. Okay, I'm going to write that down here for you. Here you go. Did you get that? That's a qualitative idea of the mass spectrometer. Okay, now we're going to delve into the mathematical details of this device. Okay, so here you go. Another important device is the mass spectrometer. The mass spectrometer is made up of a velocity selector plus an external magnetic field. For you to understand the mass spectrometer, you must first understand the velocity selector, okay? In the region of the velocity selector, only certain particles with a given velocity, V equal to E over B, exists. Exit the volume of the mass spectrometer. Outside the velocity selector, we have a region of uniform magnetic field, with the particle being subject only to the magnetic force. It will describe a circular trajectory. Outside the velocity selector, we also have two screens made of phosphorescent material. Once the particle strikes the phosphorescent screen, the screen produces a flash of light, similar to the northern light, that can be seen with the naked eye. The operator then measures the distance of this flash of light to the exit slit, okay? And find the charge to mass ratio of the particle. And then now let's go ahead and do the derivation of this charge to mass ratio and how it works. Okay, so here you go. I have the equation for the magnetic force right in here. The equation for the magnetic force is this one here, right? We do know that magnetic force is like a centripetal force that can be given by mv squared. Don't forget the particle is undergoing uniform circular motion, right? And the centripetal force is given by mv squared over r. Just like we study in physics 6. Just like we study in physics 6. Okay. And now we are left with this, with this equality here. With this equality. Right? Assume that we do know the velocity of the particle because we use the velocity selector to find out what the velocity of the particle is, right? It's E over B. And by the way, this one here, I'm going to call it the outer. The outer magnetic field doesn't have to be necessarily equal to the inner magnetic field, right? Within the volume. The V here cancels out with the other V. Let me go to the next. V here cancel out with this other V. And then you can divide you can pass the mass to the other side, right? And pass the outer magnetic field to the right side. Let's not forget that V is the electric field divided by the inner magnetic field. Okay. So now we got this relationship, the charge to mass ratio or the mass to charge ratio. Just by measuring the radius of curvature of our particle. And see here, no? This one we can measure. This one we adjust. This one we can also adjust, and this one also we can also adjust. Okay. And just by measuring the radius, we can find the different charge to mass ratio or mass to charge ratio. Okay. That's what the mass spectrometer is all about. Here you go. Here we have different particles undergoing different trajectories. In this case, he didn't put a velocity selector in there because we have an ion source that's already projecting those particles at a given velocity, okay? Here we go. And that's what we have all the way up to section 21.4. So let's take a look here what we covered so far. Twenty-one point 21.2, 21.3. It's motion of charged particle in a magnetic field. Motion of a charged particle in a uniform magnetic field, okay? B field. Uniform circular motion and uniform circular motion and helical motion. And the other one was, you know, 21.4, the velocity selector. We don't have the velocity selector there in the book, but now you have here in my notes, and the mass spectrometer. It's 11:15 already, huh? Let's take a little break now before we proceed with this chapter. So here go, break. 11:15 a.m. to 11:30. Any questions before you proceed? Okay, so I see you in 15 minutes. Okay, I'm back here. And there is another nice video here that I found showing the velocity selector. Let me show you. I'll try to play it very quickly. Okay, so you don't spend too much time on that. And this video is on YouTube as well, and show an actual experiment being performed with a velocity selector. Here you go. Velocity selector. Let's raise the volume here.
Which will be produced here by thermal emission and accelerated. I have that.
Okay, let's start from the beginning, right here.
This is a demonstration of a velocity selector. I'll be using an electron beam, which will be produced here by thermal emission.
Okay, the electron beam is produced here, and it flies, and the electron beam flies along this direction, right?
And accelerated. I have that plate there in a vacuum chamber.
Okay, we have a parallel plate in a vacuum chamber. So one is going to be positively charged. This one at the top is positively charged. See the red cable, right? That's going to most likely going to a power supply. And then we must have the black cable here. Applying the electric field. So the electric field is from the top to the bottom, right? The electric field line is from the top to the bottom. But we can also apply a magnetic field to this configuration as well. Let's see.
Slightly offset so that it cuts across the beam, and that will produce a nice straight line where the electrons are striking the plate. The plate will glow blue where electrons strike it, so we'll be able to detect where the electrons are landing on the plate. Above and below that plate are a couple of parallel charge plates. I'll be able to control the electric field over here, so we can see the electrons deflected by the electric field. Over here is another power supply which will supply current to these 10-volt coils here.
Okay, so now we have those coils here that produces a current. You're going to learn later on there is a way to produce a magnetic field with electric current. And so those coils here is producing a magnetic field that's going to be perpendicular to the electric field that you see in those two plates, okay? So it's possible, like I said, you already know how to produce an electric field, right? And now in order to produce a magnetic field, we use an electric current. And this coils here is, is the one that's used to produce the magnetic field. The magnetic field is either is into the no, is out of the plate, out of the screen in this case, okay? In this case, the magnetic field is out of the screen because we have an electric charge, negative charge going from the right to the left, okay? And because it's a negative charge, the magnetic force has to be downwards and the electric force has to be upward. You're going to see that.
So we've got a couple of coils. When we get current flowing through there, we'll get a roughly horizontal uniform field there. So we can then see the deflection of electrons by the magnetic field. And then we'll put the both fields on together, the electric and magnetic in there. And we can see that it's possible to have the electrons largely undeflected as they travel through both fields. And that gives us a way of selecting a particular velocity of charged particle in our base electrons. Tell me, supply.
Here you go. Now he's turning off the light so you can see the beam of electrons more easily.
It's our cathode filament up on the right-hand side there, lit up. That's producing our electrons.
The electrons are being produced here.
With the first light.
Here you
So
go.
you can see where there was a white light, which is coming from the filament. Now we have a blue line there, horizontal, which is
Okay, the white light, the electrons are coming from this white light right in here. Is the filament, white filament, and this blue line is the path of the electrons. They are moving in a straight line. We cannot see the plates, right? The plates are one at the top, the other one is at the bottom, and we also have those coils that you saw that are producing the magnetic field.
our electron beam. I'll start by now increasing the electric field.
He is going to increase the electric field now. Right now, the plates that you saw here are uncharged. Okay, but he's going to increase the electric field. The beam of electrons are going to be deflected upwards.
Here's the deflection.
Here you go. No magnetic field yet. No magnetic field yet. Electric field only.
That's our deflection there. Now, the electric force on the electrons is vertically upwards at all points, even though the electrons are being deflected from the horizontal and then their velocity vector is gradually increasing as they go from right to left. The force remains vertically upwards. That's the electric field deflection.
Now he turned off the electric field. He turned off the electric field. So the beams just move straight, right? And now he's going to turn on the magnetic field with the electric field off.
Magnetic field deflection.
That's the light of the magnetic of the current of the device that provides the current that produces the magnetic field. We see the deflection of the electron beams due to the magnetic force only.
The strength of the field, the electrons are increasingly deflected downwards. This force behaves differently. It is always perpendicular to the velocity of the electrons. So as they get deflected downwards, their velocity vector starts going downwards, the force will move as well with that velocity vector. It will always be perpendicular to it. So with a magnetic field deflection, we'll get the circular motion as long as they're in that uniform field. So with an electric field, we don't get that. The electric field, the force due to the electric field is always perpendicular to the plates, no matter what the electrons are doing. Okay, we can turn that one off. So
He turned off the magnetic field.
we have two forces. If we combine them, then I'll turn the if I turn the electric
Here you
field
go,
on first,
electric field.
we've now got a deflection vertically upwards. And if I increase the field now,
And now he increased the magnetic field.
going back.
Net force equal to 0. Straight line, right? Electron beam is moving in a straight line.
Now I have both forces equal in magnitude. The electric force is upwards and the magnetic field is downwards. That gives me the forces cancel out so that I maintain that horizontal line there. And the magnetic force is equal to the flux density V times the charge times the speed of the electrons. The electric force is equal to the charge times the electric field strength. If those two are equal to each other, then we can say BQV equals QE. The Q's on left hand and right hand sides cancel out, so that we have an expression with that we can rearrange for V, and V will be equal to E divided by B. So we're selecting the velocity of charged particle. Anything that travels through here undeflected has a velocity equal to the electric field strength divided by the magnetic flux density.
Okay, so that's what I want to show you. This is real life physics, okay? Now all that theory applies to real life, and that's how we explain it. And what I want to do next, let me give you a link to this video as well, right? I like this video. Video of the velocity selector, video of the velocity selector in YouTube. We are going to do an example of magnetic force, and okay, given a particle of charge Q, mass m, and velocity v, subject to a non-uniform magnetic field, only to a magnetic field. Let's see here. The velocity, okay, the velocity vector is perpendicular to b, okay? Velocity vector, not velocity selector, right? Find the radius of curvature of the trajectory of this particle. The particle is subjected only to the magnetic force, okay? Given Q and M, find the radius. Given Q, M, and B. Q, M, V, and B, find the radius of curvature of the particle. You already know the particle. Here you go. Okay, a charged particle subjected to a moving charged particle subject to a magnetic field perpendicular to its velocity vector will undergo a uniform magnetic field. Will undergo uniform circular motion. Okay. The magnetic forces is given by, that's the magnetic force, QVB. Okay. The magnetic force is the only force acting in the particle. The B force is the only one acting on the particle. Consequently, we can write down that the net force is equal to the magnetic force, right? Here you go. I have to put the net force before the magnetic force here. Here you go. And the magnetic force is given by this QVB, right? And because the particle is undergoing uniform circular motion, net force is going to be mass of the particle, the charged particle, times the centripetal acceleration, which is mass of the particle times v squared over r. I want to know this guy right here. Okay? That's what I want to know. So So this is like that. I'm gonna summarize, right? Given Q, M, V, and D, find R. That's what we want to do. That's what the problem is proposing you to do. And now I can get everything that really matters. We know Q. We know Q, V, and B, right? I'm going to put everything that we know in red color. Okay. We know M, Q, V, B. We know M. We know V. We do not know R. Okay. Next. V cancels out with V. And then we solve for R. That's the type of problem that you might need to solve. Radius of curvature of the path of the charged particle, mv divided by qb. Okay. The stronger the magnetic field, the tighter is the radius of the orbital radius of the particle. The faster the particle goes, the larger the radius is. More inertia, right? The particle has more inertia. Consequently, it's going to curve less. More inertia given by the mass, right? The larger the radius as well. The larger the charge of the particle, the larger the magnetic force, so the smaller is going to be the radius of curvature of the path of the particle. Okay, we're going to go for another example here, example 2. Find the period T of translation of this electric charge. How long does it take to complete a full orbit, okay? Of the above electric charge. Okay? So the full circumference of the path of this charge is going to be given by, we need that. We need to know this full circumference, right? Because we need to find the period. Why is that? Why is that we need that? Well, there's a very good reason, right? So before we go the full circumference, just remember that I'm gonna write down here. Here you go. V of a given particle is going to be, the full circumference divided by the period, right? That's why I need the circumferential length of the particle. Full circumference is 2 pi r. Okay, 2 pi r, we found that r is mv divided by qb. Solution, right? I'm gonna write that down here. Given, given qmvb, now we already have r, right? And r, we found r previously, comma, find t, period of revolution of the particle. And now all I have to do is now substitute C there at the top. Don't forget, I'm going to emphasize that we're trying to find PT, right? The C full circumference is that. We go We do not need the V anymore because the V here cancels with this V. I don't need this intermediary step, but I can isolate T. Like that. That's the period of oscillation. That's the period of full, not period of oscillation, there's a period to undergo a full circle. Okay. The stronger the magnetic field, the shorter the period. Okay. And now going back to the book. Here you go. Force on a current in a magnetic field. On a current in a magnetic field. Okay. And that's what I'm going to cover now. Going back here to our there you go. 21.5. Magnetic force in a current. In a current. Force on a current, a magnetic field, right? Well, so here you go. You know, since a moving charge experiences a magnetic force, then it is straightforward and let's say and an electric current is nothing but moving charges. Remember that? Then we conclude that a current, a wire, let's say a wire carrying a current carrying wire, let's write that like that. A current carrying wire will also experience a magnetic force. Make sense, right? So let's see if I can get that here. Let's see if I have an illustration here. Okay, yeah, current carrying wire. Okay, suppose that we have this small section of a wire that's carrying a current. Okay, we have electrons moving from the right to the left, right? Electron moving from the right to the left are going to experience a downward force. Make sense? Current from the left to the right, motion of the electrons from the right to the left. We go ahead, do the V cross B, which is upward, but then because we have a negative electric charge, the force must be downwards. Make sense? Here you go. Whether we do that either for the electrons moving from the right to the left, or we do for the current flowing from the left to the right, and we still get the same force. B field here. Oh, magnetic force. Yeah. Magnetic force. So the wire will tend to bend. But what is the exact equation, right? There's an exact equation in terms of the current that we can write. Okay, we start with the magnetic force. Start here with the magnetic force, QVB sine of theta. But remember, but very important, we can go ahead and here write our equation. Let's let's do this way. We put a delta FB here, and here we put a delta, oops, a delta Q here as well, right? So let's say we have a magnetic force in infinitely small amount of charge. We have this infinitely small magnetic force, right? And here you go. I'm going to here write like that. And now, see, I have delta T here and delta T here. Consequently, I didn't change anything which was in this equation, right? Let me emphasize that for you here. Delta T here and delta T here. Let me emphasize that. But now, take a look here at this V delta T. This V delta T is nothing but a small delta L in the conductor, in the wire, conductor wire. And this delta Q over delta T is nothing but the current, okay? We have an infinitesimal amount of magnetic force in an infinitesimal short conductor. So we can then, for the conductor is the length L, we can end up writing this equation like that. Okay, here you go. Here's the equation for the magnetic force due to a uniform, by the way, this is a uniform magnetic field. Okay, magnetic force of a due to a uniform magnetic field in a current carrying wire. Has uniform, don't forget. If you were not uniform, would be a little bit more complicated this equation, right? I did that for a uniform magnetic field. So there are some applications for this type of phenomenon. And what's that? Speaker. Let's take a look. The speakers that we have in sound systems utilizes this type of phenomenon. This utilizes this type of force. Okay. And here's an illustration of what happens to a current carrying wire subject to a magnetic force. We have a demonstration there also at the college. We have this wire right in here. Whenever the current is turned off, it's it's in the vertical direction. When you turn on the current, it ends up being deflected. Okay. And we have this practical application, okay, of the magnetic force in a speaker. Okay, so here you go. We have this magnet, north here, south surrounding it, right? Here's the north, here's the south, and this cylinder is fit into this gap here. And along the cylinder, around the cylinder, we pass those wires. Okay. So what do we do? This is a power supply that we vary our current. We can make it stronger or smaller. Okay, and this is the direction of the force on the speaker. Can go up and down, right? So here you go. Do the V cross B here, right? V cross B. That's B. Here you go. Is this lower end here of the speaker has a force to the right. Similarly, V cross B, the other upper region also is going to have a force to the right. So as you change the direction of the current, this thing keeps oscillating back and forth. Force to the right, force to the left, force to the right, force to the left. We can change the direction of the current with a device like that, okay? And make the speaker vibrates in the horizontal direction. So here you go. Basic components of a speaker, right? I'm gonna document here my notes for you. Basic components of a speaker: a permanent magnet, a source, a current source, a source of current, a source of current that oscillates, that makes the current, a source that makes the current vary back and forth. That's what we call alternate current source, AC. A cone coupled to a cylinder. The cone is the speaker, right? And a conducting wire around the cone. Okay. What else? The conducting wire is subject to the magnetic field of the permanent magnet. Okay. When the current in the wire is zero, there's no magnetic force whatsoever. However, when we turn the current in one direction, a magnetic force is applied to the wire in a given direction. Let's say to the right, just like you saw in there. When this current is reversed or inverted, the magnetic force is inverted as well. And that produces that oscillation back and forth of your speaker. If you can make this vibration very fast, 20 hertz, 30 hertz, 40 hertz, 1,000 hertz, 5,000 hertz, all the way up to 20,000 hertz, you do end up producing a sound that will have a frequency of vibration of your cone, okay? Depending on the frequency of oscillation of your current, okay? The cone of the speaker is going to move back and forth at the same frequency, at the same specific frequency. These different sound frequencies, right, can be produced by varying the frequency of the current. Remember, right? Remember that the frequency we can hear is between 20 hertz and 20,000 hertz. So just by putting my current to oscillate within this range, we can produce sound frequencies within this range as well. That's the principle of the speaker. Okay, what time is that? Oh, 12:03 already. Okay, folks, I ran out of time here. Any questions? You're still there, right? We cover lots of material all the way out to 221.5. Here you go. We still all cover the torque on the current next time, magnetic fields produced backward. That's important. That's important, okay? And then Ampere's law. We're not gonna cover this one. Okay. So we can stop now and I'll see you the day after tomorrow. Thank you for being here. Not three.
Professor, can you hear my voice?
What was that?
Can you hear my voice?
Yeah, they can.
Yeah, my mic wasn't working for a second.
Yeah. How may I help you?
So Professor, I need help with the downloading process. Can you give me the power to share my screen?
Yes, let's see here. Let me stop sharing here. What do we need again? I didn't understand what you need.
The downloading process, a specific page that I can't remove.
Okay, go ahead. You
Okay.
can share the screen. Go ahead. Let me stop.